All right. Thank you very much. My name is Matthias Specht. I'm the lead developer of the CGA team here in Zurich. And I'm going to present you the new CGA features in the upcoming CityEngine 24.1. So first, I'm around since day one in CityEngine and CGA. And I'm super amazed to what you guys do with it. So if you guys, I mean my fellow presenters, these were really, really impressive things. And I'm equally amazed or excited to show you the new features we're going to release now. These are the biggest features in CGA for quite a while. I think they're true game changers. They will affect how you write CGA or what you can do with it. Here as a teaser, you see a few images. So probably most of you would agree that the features on the right are not typical CGA models. The one on the left looks a bit more like a typical CGA model, but still there are a few things in there which were not possible so far. So let's just jump into it. First, we are going to look at how to model a hashtag shaped building. So you already see here three initial shapes with models on them. You see the rule on the left. It's a simple, typical CGA rule. The initial shape gets split in 2D into a grid, basically. So it's classic split. Then there's a bit of magic with the cell indices. Some cells are nilled, and you get a hashtag. So that's pretty cool. However, there are a few limitations here. So let's say we want to put a roof on the building. Of course, straightforward. We put a hipped roof on there, but this is not what we wanted. We wanted to have a roof on the building, not many buildings with a roof. In fact, our hashtag consists of several buildings, not one building. This is also obvious when we look into the models. There are many faces inside this building or in between the buildings. So we are kind of limited here to subdivided shapes. That's the nature of this rule, right? The first thing we did is we subdivided the initial shape, and here is what we get. We get many shapes. We get a shape tree with independent shapes. This is how CGA works. It's all good. But in this case here, we actually wanted to have one building, not many buildings. So yeah, what can we do to overcome this? Well, one solution or approach could be to actually export this result of the CGA rule and then re-import as one shape. So let's do that. We just export it to an OBJ. So now all these separated shapes become one OBJ, one geometry. We changed the rule a little bit to import this OBJ. You see, there's no splitting anymore. We just import an OBJ. Visually, it still looks the same. But now it's just one shape. So yeah, I guess you're all familiar with these things. Now we have the whole geometry in one shape again, and we can continue. Basically, we can continue working on this building. So, for instance, we can do a cleanup geometry to get rid of all those coplanar edges, and then we can fire up our building rule again and get this time one building. So all the roofs are connected. There is no internal faces anymore. We have a nice and clean geometry. So this is what we actually wanted. However, this thing with exporting and re-importing, I mean, I saw before some people here are true Python wizards. They can easily script that into Python, but still, it's not. It kind of broke our CGA workflow. We had to basically start from scratch again. But here comes the new thing. We now have a new keyword, inline. This basically does what we did before manually. We can just use the result of the hash rule as one shape. Inline executes the rule, collects all its leaf shapes, and puts them together again. The patch there indicates that all the geometries are just copied into one, just appended into one geometry. So you see that now, if we look at the result, we can do the same thing as we did before after re-importing it. So we can just continue in the same rule with, on the result of the first rule. The hash rule there became something like a shape operation. We can just continue. We can put the roof on there, and there are no intermediate phases anymore. So let's recap this quickly. There's a new functionality called inline. Inline undoes the subdivision. So CGA is by nature subdividing things, be it the split as here or the comp split. Now we have a way back. We can just inline it and work on the results. So this allows us to kind of chain or sequentialize several generate steps. All right, but there are still some limitations. Let's look at our nice hashtag house now. Well, what about the other parts of the initial shape? So we kind of split off a few things by nilling away other things, but maybe we want that courtyard there. Maybe we want to put a playground in there, and the other faces around there. We want to put plants there. These faces are lost because we nil them. So we maybe could. Oh, what can we do? We can use tags. Here, this is the new rule. Tags were introduced a year ago, but now they become really, really useful. So you see, instead of nilling the shapes, we tag the faces. Tags can be put on any geometrical components like faces, edges, vertices. In this case here, we put a tag on a face. We inline the whole thing. Geometry looks like the grid. The whole grid is there. All the geometry is there. But some faces are tagged. That's not visible. If we clean up geometry, we see only the coplanar edges between faces with the same tags are removed. Then we can use comp split to take out only the parts of the geometry we actually want. So you see, building are the ones we used before. It's the actual building footprint, but then there is the outer faces and the court in the center. So we can distinguish between those geometries, those faces. We have a semantic tag on them, and we can use the comp split to assign different rules to them. Continue. And of course, if we enable our building rule again, we get the nice house. We still want more. what about the facades? Now we just have a facade rule there, but maybe we want to distinguish them. For instance, those in the very front there, where the mouse pointer is now, they might be facing a street. So maybe we want to put a different facade there than the ones facing our green garden. Or the court. We want to know which facades are facing the court. We might use a completely different rule there. So how can we do that? Answer is we can use edge tags. So here you see the facades of different colors. We did that by adding tags on the edges this time, not the faces, but the edges. So let's see. Yeah, there's the operation. That's a new one. Before we weren't able to put the set tags, and now we can choose which geometry we want to tag. Here, obviously, it's the edges. And first we tag the edges around the border of the initial shape. That's what's highlighted now. But then we also put a tag on the edges of the chord in the center. Now, these component tags, they are propagated across inline, and they are propagated across shape operations. So even if we do quite a lot of things with this geometry, in the end we are able to exploit the tags and use them for different facades. Here the edges were tagged, but when we extrude a face, the extruded faces get the tags from the edges. So in the end, we can just ask the facade if it's a border or a chord facade. Okay. So let's recapitulate that. Component tags give context. Component tags can be stored in geometry with the tag operation. They get propagated across operations, and they can be exploited with the comp split later on. They can be used to choose the components which should be used in the follow-up rule. Okay, but there's even more. We introduced 3D booleans. Let's just have a look. It's a nice little scene. My colleague Niklaus passed me today. He's kind of the inventor of all these things. And you see, this is pretty obvious here. We have classic Boolean operations, cube, the sphere. We union them, we subtract them, we intersect them. On the left is the union. So you see clean geometry. It's all watertight. Inside, there are no faces. Yeah, you see, it's all in CGA. There's no, I mean, of course, we use primitives, but we don't, it's all calculated inside CGA. Here's the subtract, where the sphere is subtracted. And then, of course, you might want the other result, the swap parameter to get the other part of the subtraction. Or just the intersection. And then again, you see tags are used. In this case, they are so-called auto tags. The Boolean operations set tags, which can be used to know from which operand operand mesh a specific face is coming from. So that's then used to color it. So here's a different example for such a Boolean operation. That's a pretty cool mass model. Here you see also, it's a super short rule. There's not much. It's very nice. It's part from our CGA reference actually. That's why it's so super nice and clean. Here you see that we use the tags set by the extrude operation. So all operations set tags. These are the auto tags, and they can be used to then take apart the geometry to know what's what kind of phase you're dealing with. Here's another cool maze model. For me, it's the sliced house. Niklas called it the office building. Yeah, this is perfect maze model for a super fancy office building. I hope Israel is going to build that here in Zurich. Okay, here are some more inspirations what you can do with Booleans. The classical things. Here you see that they also work on 2D. So you can also use 2D polygons and combine them with the Booleans. So yeah, let's step through. This is the input, C2C fighting, the overlapping polygons. We unify them, and we can again use tags to distinguish the different areas. Finally, if we extrude it, tags are passed on, and we can exploit them again. Okay, there's a pretty cool maze model here. Here again, let's see how this is constructed. So it's a very nice rule where we can choose the construction steps. So on the first, let's see the initial volumes which were used. This nice model. So we start with a cube and a sphere. Pretty straightforward. Then we intersect it, and we get this cut sphere. We go on, we split it into two parts. You see again the tags that are used to color the two parts. One half gets shifted a little bit, and then it gets actually, with inline, it gets actually put into one shape again. So you see, we can really sequentialize our generate calls. Next thing is we put on a cylinder there in order to subtract the hole out of our nice mass. Yeah, so this could be a mass model for a very interesting landmark building. Again, you see the tags are used to then color the different parts of it. Yeah, let's recap this. We can now use 3D Booleans to model solids. This is pretty much based on the concept of inlining a rule. Here you see the syntax. If the keywords union, subtract, intersect, you just add a second operand, which is a rule. This rule gets then executed immediately. The shapes get combined and then subtracted from the current shape. These are great tools to create maze models. Actually, I ignored a little detail there. Some of you might have seen it in the code of the last example. There's a second way for inline, a second mode. So if you look at these nice stairs here, recursive rule, again, a very small, short rule. It's also a CGA ref example. If we look at the stairs, they are actually overlapping geometry because we use this append. We just copied all the geometry on top of each other. It looks quite good, but we can also use a different mode, unify. Unify, let's check it out. Zack. There you see it actually cuts, it uses the union operation to create a nice, clean, watertight volume. Okay, so there are two modes for inline. One is append, which just copies all the geometry. Often this is exactly what you want. And there's another one, unify, which uses the Boolean union operation. This is, of course, great if you want to create watertight mass models. So overall, we have a trinity of new CGA features. They all work together. Each of them is powerful, but the true power is the combination of all of them. Rule inlining, component tags, Boolean operations. There are actually much more examples in the CGA reference. And there are way more things possible than I showed you now. This was just a basic glimpse. We just released a beta version because the CGA ref is not online yet. If you try the beta version, check out the offline CGA ref, which is built into CityEngine. There you see the new features explained, and you see examples. You see there's a whole section about rule inlining and Booleans, the tag operation. And actually, I don't know if you can read it, but there's also an example, best of two alternatives. This has nothing to do with Boolean mass model generation. This uses inline to explore two different paths and then choose the best one. Inline really gives you a lot of new possibilities, how to write rules, how to deal with it. Yeah, all these new things here were presented in a SIGGRAPH paper in this summer in Denver. So it's all based on bleeding edge research. We are very proud of it, of course. If you look at the teaser images here from the paper, you might recognize some of the examples which we looked at before. But if you have a closer look at this paper, you might also notice that not everything for the paper is already implemented. Means it could give you a hint of what we're working on. I really recommend you to Google for the paper because there's also a very, very nice video. It's around, it's easy to find, and it explains all the stuff I talked about in much more detail. And yeah, actually, there's one more thing. Let's say we want to, as we always do in CGA, we model a facade. A facade needs a door. Door is important. We take lots of care. We put on a nice handle, a very detailed handle, hand modeled in Maya or whatever. But what's that? If we look at it very close up, we might notice it doesn't look like the one we just modeled in Maya before. There's a new thing, a new parameter for the insert operation. You see, this is how it looked in Maya. This is how it looked in CityEngine. Now you can use the no cleanup parameter to avoid any the insert changing anything on your asset. This is a notorious problem for people which use very, very detailed meshes. And because we improved the internal precision of our geometry processing, we can now improve things like this. This is the first step. I'm sure some people will like this a lot. Yeah, that's it. As mentioned, beta just came out. Check it out. And thanks for your attention.
Very cool stuff. Let's see if there are some comments or questions. Not a lot, I think. Matthias, I think you baffled everybody. Congrats on all of the advancements. This stuff is massive, obviously, and you guys have been working on that stuff for years and years, and it's it's a massive step. So kudos to that, and definitely looking forward also to the rest of the things you just mentioned that are coming in, that you implied are coming based on the paper.
Yeah, thanks. I'm very looking forward to see what you guys do with it.
You will. So a person is asking, Brian is asking, can we post a link to the SIGGRAPH paper in the chat?
I can look it up.
Okay. Yeah, let's do that right now. I just downloaded the beta, I think yesterday evening, 2 days ago. I'm not sure, but I didn't have much time to play with it. So, all right. So there's the link. I'm gonna post this one publicly. All right, link is posted. Sweet. Yeah, but it seems there are no more questions coming in right at the moment. I think the examples were pretty clear, and it's probably best to get the hands dirty yourself, right? And there's a thank you Matthias squared that just came in. Very cool. Yeah, so thank you so much, Matthias, for that for the presentation. This has been really cool. Yeah, but I would like to just open it up pretty much for a few more questions or comments or thoughts. All right, so there's we just got a question from Patrick, who presented before, and the question just disappeared. Where is it? How does reporting get propagated using inline? That's a good one.
It's a good one, yeah.
Nice.
It just gets summed up. So basically, inline basically generates a sub shape tree. It's a bit technical, but I have to go there to explain it. This shape tree gets collapsed into one single shape, and all the reports and prints and so on are just assigned to this new shape. So it's basically the result of this of the rule you inline. All those reports, they are still around. They just seem to come from the one single inlined shape.
So at the moment you mentioned they are summed up, kind of, which potentially at the moment, so if they are summed up, would it be possible or to basically also say how they should be computed instead of just summing them up, maybe take the average or create rules for how you want to propagate that?
I wasn't entirely correct. It's not sum up, it's append. So they are collected and you get the whole set of them. And I just realized if reports, we also have the sum operation. It's not a mathematical sum. It's just you co-report twice, you get two reports. And then of course, if in the inspector you look at the sum, then it's the sum, but it's still, as you said, if you want to see the average, then it's the average.
All right, there's another comment coming in from Nikolai. He says, I've been looking into Visual CGA a bit. It seems to do visually what the import function has done so far, linking different CGA script. Is import going to be deprecated in favor of start? It seems that the two do parallel things, which means that you have to opt for the one or the other?
Well, that's an excellent observation. Yes, VCGA is based on imports. It's true. All those nodes you place in VCGA under the hood, they are imports. That's true. Great observation. But no, it's not going away. VCGA completely relies on the import functionality from CGA. And the start rule, as mentioned, is important to describe the interface this imported rule set. So you need to know which is the start rule of a component. So both things are really extensively used by VCGA together with the extension rules. But nothing is going away. It's made to stay there. I hope that answers the question.